Okay, so electron dot diagrams. Remember, we need to make sure that they have how many electrons in their outer shell? 8, right? So that's the goal, to get everyone having 8 electrons in their outer shell, and then you need to be able to work out how many electrons are within the valence shell of each element from the periodic table. Happy with that idea? So if I say nitrogen, how many electrons are in its valence shell? You'd look at a periodic table and you'd be able to tell me that there are how many? 5. Yeah? Are we happy with that? We all know how to do that?
Yes.
Yeah? Because of the group number and stuff? Yeah, okay, cool. All right. So let's go through how to draw these electron dot diagrams, and we'll start off with the easier ones. Okay, so the easiest one will probably be this HCN. Okay, so remember, H has 1 electron, carbon has 1, 2, 3, 4 electrons, and the nitrogen goes 1, 2, 3. Okay, so how do we remember the steps that I gave in terms of how to draw electron dot diagrams? I can't remember the steps. What are the steps?
You work out how many electrons are needed.
Yep, how many electrons are needed? So how many electrons are needed for this HCN? Of this H, sorry. 1. How many electrons are needed for this carbon?
4.
How many electrons are needed for this nitrogen?
5.
5. Okay, now what? No, wait, not 5. Yeah, 5. No, I've done that wrong. How many? There are 5 electrons on that nitrogen, which means that this needs how many?
3.
3. That's better. Okay, now what?
You draw lines.
Draw lines. Okay, so you will draw a line for each one there, for each element, for 1 line for each electron needed. So if it was SO2 here, I would draw S, which needs 2, and oxygen that needs 2, and oxygen that needs 2. Okay, so there are 2 oxygens, so that you have to draw 2 of them there. Since all of them have 1 here, you don't need to draw that one there. Okay, so now that you've drawn those lines there, what now?
Join them together. Connect them.
You connect them. Okay, so this is the tricky bit, but with a bit of practice, you will see how they generally go together. Okay, now what? I've connected all the lines, I've followed the rules. Do you remember what the 2 rules are?
Remove the lines and add.
Sorry, what? And then what are the rules? What are the rules when you're drawing these?
It can't connect to itself.
Can't connect to itself, and
Can't leave any unconnected.
can't leave any unconnected. Cool. So now what you're doing is you're imagining that these lines become shorter and they become like nice and straight. So they just go H, C, N. Happy with the idea that there are 3 lines connecting that C and that N, so there are 3 lines there. Okay, now what's the next step? Replace the lines with X's and O's, good. Okay, each line is replaced with a pair of electrons. Okay, now what?
You add any additional.
Add any additional ones. Okay, so the hydrogen here, that X there is that X there, so that's fine. That carbon has 1, 2, 3, 4. It's got 1, 2, 3, 4. And then this nitrogen has 1, 2, 3. It's supposed to have 5, so how many do I need to add more?
2.
2. So you need 2 more. 2 more here. What the? You need 2 more here. Okay, so therefore it looks something like this. H, C, N. Okay, and I really should have flipped those around, but yeah. Okay, so that's that first one, HCN. Okay, so let's move on to a slightly more difficult one. Let's do the
So this
SO2.
one is wrong.
That one is wrong there, okay, because it doesn't have the extra one there. So actually there is no correct answer in this one. I think a dot got deleted somewhere, somehow. Okay, cool. All right, so let's go on to this SO2. Now hopefully you remember your coordinate covalent bonding as well. So sulfur and oxygen both have 6 electrons in their outer shell. Okay, which means that they need how many?
2.
2. They all need 2, which means that you're drawing S with 2 lines, O with 2 lines, and O with 2 lines. Okay?
So the lines represent how many more
Electrons
they need?
Yep. Okay. Right. Now, this one here can't really be done with the normal one. Like, I mean, it can, because you can do this, right? There and that one there. And you would end up with this weird SO triangle, which, like, you know, in theory could exist, but it doesn't, all right? So generally when we have something with lots of O's in it, it's generally going to have coordinate covalent bonding, all right? Bit hard to say when, but coordinate covalent bonding on all of your substances with lots of O's generally on it. Okay, so what you then have to try and do is you have to say, okay, well then, let's just start putting these things together using double bonds, and we'll work out at the end how we're going to put the rest of them together. Okay, so this sulfur could form a nice double bond with this oxygen. Are we happy with that? That sulfur could form a nice double bond with this oxygen. Now remember, coordinate covalent bonding, the idea is that this oxygen here could use a couple of electrons from that sulfur there. Okay? Because the idea is that the oxygen is quite electronegative, and so therefore it's going to just kind of grab onto those ones there without sharing any of its own. Now, how many does the sulfur have? The sulfur has 8. How many does this oxygen have? It has 8. And how many does this oxygen have? It has 8 as well. Right? So that could be one way of drawing that sulfur dioxide with coordinate covalent bonding. Okay? It's a bit hard, but generally when there's lots of O's like NO3 or SO2 or SO3, they will have coordinate covalent bonding, where you just start with the central atom, you double bond it to as many O's as you can, or you have to, and then you work out how they add extra ones to it via coordinate covalent bonding. Let's try this one here, this NO3 minus. This NO3 minus, remember, is a polyatomic ion, which means that it's going to have this negative charge, means it's going to have how many more electrons than it should have? One more electron, yeah? So therefore, this remember, how do we work out this one here? What are the steps? For every negative charge, you anticipate that it's going to be a hydrogen. So technically, this is the same thing as that, except without a hydrogen, because you can just remove the hydrogen at the end. And then you can redraw this HNO3. So you start off with the central atom, which is the N. And remember, for every hydrogen, there is an OH group. So that OH group is OH, there, coming off the nitrogen there. And I'm just going to replace those lines with dots and crosses to make this a bit easier. And then I show that the oxygen has the 6 proper electrons there because it has 6 orbital of its own. So that's what we mean by every hydrogen has an OH thing there, which you draw that one there. The nitrogen had 5 electrons. And so you've got to see that this nitrogen, does it need more electrons? How many does it currently have in this diagram? 6, which does that mean it needs more? Yes, it does. So how is it going to get more of those electrons? It's going to double bond to oxygens, okay? So that's how it gets this extra electron. So it double bonds to an oxygen. Now it has how many? 8, okay, which is what it wants. That oxygen,
sir,
yep.
If that had 6 before, why can't you just draw 2 more at the bottom?
Because remember that this nitrogen, these are the 5 electrons that the nitrogen has. Like this nitrogen has 5 electrons here. Okay, so if you were to just draw extra ones, you'd just be drawing them out of nowhere and they wouldn't come from a certain element. Okay, so it's got a bond to get those extra electrons. Okay, so then you've got this double bonded O here. You've still got 1 more oxygen to do, right? Because you've got 2 oxygens, but you've got 1 more there, right? So therefore, does this nitrogen need any more? No, it doesn't, which means that it can coordinate covalent bond to this oxygen, where this oxygen is going to use those ones there without giving any back. Okay? Now, I haven't finished this yet. What I've drawn is this, but what I was asked to draw is that. So how do I go from that to that? Put brackets, that's the first thing, it's good. And show that it's a negative charge. And what do I need to get rid of?
H.
That H, okay? So I get rid of that H, and now it looks like that. Okay? And then finally, the other easy one, or kind of easy, is this NaCl. Okay? This NaCl, how do I know that this is an easier one? What should I?
Ionic.
It's ionic. How do I know that it's ionic?
Metal and non-metal.
A metal and non-metal. Okay, so if it's ionic, remember, what do we have to draw for ionic electron dot diagrams? What are we drawing? Got to draw square brackets. One's going to be a minus charge, one's going to be a positive charge. Which one's the positive charge?
Na.
The Na, and the Cl minus is the negative charge. What else do I have to draw here?
The electron.
The electrons around which one? The negative or
No.
positive? Sorry? The positive? No, because the positive element, that Na started off with 1, and it gave away that 1 to the Cl. So now it doesn't have that 1 electron there, and it's turned into a positive ion. So that means that that Cl now has 7 of its own, because that's how many it started with, and 1 from the sodium. Okay? And that's what you would draw for that NaCl. Any other examples that you want me to draw? That you looked in the thing and you were like, I can't draw. Ishika, that exam there, which one? Chloromethane? Do you want to have a go? Yes, you want to have a go. Yeah. So, what's it? Chloromethane? So, CH3Cl. Go, draw. Go, draw.
Oh, I have to do it the long way.
You don't have to do it the long way. If you want to do it the short way, you can do it the short
Oh,
way.
wait, just put H, and then CL.
Yeah. And then you convert it to dots and crosses, yes. Good. Yay. See, you're awesome.